You probably believe that with enough technology, enough data, and enough intelligence, reality can be measured perfectly. That if we just build better instruments, sharper sensors, and more precise equations, the universe will eventually give up all its secrets. That belief feels reasonable. It feels scientific. And it is completely wrong. I'm not here to argue that perfect knowledge is difficult. I'm here to show you that it is impossible in principle. Most people misunderstand this. They think the problem is human error. Shaky hands, imperfect machines, limited brains. They assume that one day those flaws will be fixed. But I'm not talking about limitations of technology. I'm talking about the structure of reality itself. At the smallest scales, nature does not allow you to know everything at once. Not because you lack skill, but because knowledge itself interferes with what you are trying to know. The act of measuring is not passive. It is not neutral. It changes the system. And this is where intuition breaks down. You imagine particles as tiny objects with precise positions and exact speeds, waiting patiently to be discovered. But that picture belongs to a classical world that no longer exists. In the quantum world, asking a question is an intervention, and every answer comes with a cost. To understand why perfect knowledge is forbidden, we have to let go of how we think observation works and accept that uncertainty is not a bug in physics. It is a feature of reality itself. When did uncertainty begin? That question sounds historical, almost innocent, as if uncertainty were discovered on a specific date, written down in a notebook, and quietly added to physics like one more rule. But uncertainty did not begin when someone wrote down an equation. It began the moment classical logic stopped working. At the start of the 20th century, physics was confident, almost arrogant. Newton's laws had ruled for centuries. Maxwell had unified electricity and magnetism. The universe looked like a perfectly engineered machine. If you knew the initial conditions, you could predict the future forever. Reality, it seemed, was fully readable. Then scientists started looking closer. Much closer. When physicists pushed beyond atoms into the realm of electrons and energy quanta, the machine began to malfunction. Not metaphorically, conceptually. Electrons did not behave like tiny planets orbiting a nucleus. Sometimes they acted like particles, sometimes like waves, sometimes like neither. Light, once a wave, arrived in discrete packets. Energy refused to be continuous. And worst of all, measurement itself became a problem. In classical physics, measurement is passive. You observe without consequence. You read reality like a thermometer reads temperature. In the quantum world, observation is invasive. To measure is to disturb. To look is to interfere. This was not a philosophical inconvenience. It was an experimental fact. And once you accept that, the entire classical dream collapses. The dream that sharper tools will eventually reveal a perfectly sharp world, because the problem isn't our clumsiness. The problem is that precision itself has a cost. To know where an electron is, you must interact with it. You must bounce something off it, light, energy, momentum. And that interaction changes the electron's motion. Not accidentally, not temporarily, fundamentally. No matter how refined your tools become, this trade-off never disappears. You can sharpen one variable only by blurring another. This insight shattered classical logic. In the classical world, properties exist independently of observation. Position is position. Momentum is momentum. Both are real at the same time. Quantum mechanics rejects that assumption. The uncertainty principle states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Not as a practical limitation, as a law of nature. The universe does not have exact values waiting to be revealed. Exactness is not hidden. It is undefined. This was deeply unsettling, because if properties are not fully determined until measured, then reality is not a fixed script. It is probabilistic, contextual, relational. Cause and effect, once absolute, becomes statistical. This is where classical logic collapses, not because it is wrong, but because it is incomplete. Classical logic assumes that things are either true or false, known or unknown. Quantum mechanics introduces a third category, unknowable in principle. I'm not trying to destroy determinism out of rebellion. I'm following the math where it leads. And the math says something radical. Nature is not obligated to satisfy our desire for certainty. At the smallest scales, reality behaves less like a solid structure and more like a set of constraints. You are allowed certain combinations of knowledge and forbidden others, not by human ignorance, by the architecture of the universe. This changes how we think about truth. In classical science, truth is about accuracy, getting closer to the exact value, reducing error bars. In quantum science, truth is about limits, knowing what questions can be answered simultaneously and which questions cancel each other out. This is why the uncertainty principle is not just a physics equation, it is a philosophical boundary. It tells us that the universe is not fully transparent to inquiry, that some aspects of reality resist being pinned down, not temporarily, but permanently. And that resistance is not chaos, it is order of a different kind. Probability replaces certainty, ranges replace points, distributions replace trajectories. The world still follows rules, but not the rules we expected. When uncertainty was born, it did not announce itself as ignorance, it announced itself as structure, a reminder that logic built for everyday objects breaks down when applied to the foundations of existence. And once that door was opened, it could never be closed again. Because if perfect knowledge is impossible at the deepest level of reality, then certainty was never the natural state of the universe. It was an illusion created by distance. The closer we look, the less the universe resembles a machine, and the more it reveals itself as a system that refuses to be fully known. So, why doesn't the electron ever stay still? After accepting that perfect knowledge is impossible, this is the next question that naturally follows. If uncertainty is built into reality, what exactly forces it to exist? What prevents a particle from simply settling down, holding a precise position and a precise motion at the same time? The answer begins with a mistake our intuition keeps making. We imagine observation as something gentle. We picture ourselves watching the universe from a safe distance, like spectators in a dark theater. Reality performs. We record. But at the quantum scale, there is no distance. There is no balcony seat. To observe an electron, you must interact with it. And interaction is never neutral. Imagine trying to photograph an electron. Not metaphorically, literally. Electrons are unimaginably small. You cannot see them with visible light. The wavelength is far too large. To resolve something that tiny, you need light with an extremely short wavelength, which means high-energy photons. And this is where the problem begins. Photons are not passive messengers. They carry energy. They carry momentum. The moment a photon strikes an electron, it transfers some of that momentum. The electron recoils. Its velocity changes. Its trajectory shifts. You have learned something about the electron's position, but you have disturbed its motion. This is not a technical failure. It is not a flaw in experimental design. It is unavoidable. If you reduce the energy of the photon to disturb the electron less, the wavelength increases. Your image becomes blurry. You lose positional precision. If you increase the energy to sharpen the position, you increase the disturbance. You destroy information about momentum. There is no sweet spot where both are preserved. This is the physical heart of the uncertainty principle. In classical physics, objects possess properties independently of measurement. Observation merely reveals what was already there. In quantum mechanics, properties are not fully defined until interaction occurs, and that interaction reshapes the system. The electron is not hiding exact values from you. Those values do not exist simultaneously, and this leads to a deeper realization. The electron is not a tiny billiard ball. It is a quantum object described by a wave function, a mathematical structure that encodes probabilities, not certainties. When you are not measuring the electron, it does not have a single position. It has a distribution of possible positions. When you measure it, that distribution collapses into a specific outcome, but the cost of that collapse is lost information elsewhere. The electron does not stay still because stillness itself is not a well-defined state at that scale. Even if you somehow removed all external disturbances, quantum mechanics tells us something unsettling. An electron confined to a precise location must possess momentum. This is not experimental noise. It comes from the mathematics. To localize a wave, you must combine many wavelengths. Those wavelengths correspond to different momenta. The tighter the localization, the wider the spread of momentum. Perfect stillness would require zero momentum uncertainty, and that would require infinite positional uncertainty. The electron would have to be everywhere at once. So the electron moves not because something pushes it, but because the structure of quantum reality forbid absolute rest. Stillness is a classical concept. At the quantum level, motion is not always the result of forces. Sometimes it is the result of constraints. This reframes observation entirely. In the classical worldview, the universe exists independently, and we occasionally peek at it. In the quantum worldview, the universe and the observer are entangled. Measurement is not a window, it is a handshake. Every question you ask the universe demands an exchange, and every answer comes with a price. This is why the uncertainty principle is often misunderstood as a statement about disturbance alone. The photon example is helpful, but incomplete. Even without photons, even without measurement, uncertainty remains. Because uncertainty is not just about observation, it is about definition. Position and momentum are related in such a way that defining one sharply erases the other. This is not because nature is sloppy, but because it is consistent. Quantum reality is not chaotic. It is precise in a different language. Probability replaces certainty. Ranges replace exact values, and outcomes replace trajectories. The electron does not follow a single path through space like a miniature planet. It explores possibilities until interaction forces a resolution. And when you observe it, you are no longer outside the system. You are part of the dance. This realization shattered centuries of assumptions about objectivity. It forced physicists to admit that knowledge has limits that cannot be engineered away. The universe is not hiding behind a veil we can someday lift. The veil is woven into the fabric of reality itself, and the electron never stays still, not because it refuses to cooperate, but because stillness was never an option to begin with. So what does the uncertainty principle really mean beyond the myth? After realizing that the electron cannot remain still and that observation is an interaction, the next mistake is almost inevitable. We hear the word uncertainty and immediately translate it into chaos, randomness, ignorance, a lack of control. That translation is wrong. The first major misunderstanding is the idea that uncertainty means pure randomness. It does not. Quantum systems are not lawless. They are not rolling cosmic dice with no rules. They are governed by precise mathematical structures that produce probabilities. And those probabilities are not guesses. They are predictions. Given the same conditions, quantum mechanics will always give you the same probability distribution. What it will not give you is a single guaranteed outcome. This distinction matters. Randomness implies disorder without structure. Quantum uncertainty is structured uncertainty. You cannot predict which exact result you will get, but you can predict how often each result will appear. Over many measurements, the pattern is stable, repeatable, and astonishingly accurate. Uncertainty does not erase predictability. It changes its form. The universe shifts from certainty about events to certainty about distributions. The second misunderstanding is even more persistent. The idea that uncertainty is merely a measurement error, that it exists because our tools are imperfect, our hands shake, or our theories are incomplete. This belief is comforting because it suggests a future fix. Better technology, better instruments, better minds, but this principle cannot be bypassed by any instrument, real or imaginary. Not by perfect detectors, not by hypothetical devices built from flawless materials, not even in thought experiments. This is not a technological limit. It is a physical one. The uncertainty principle does not describe what we fail to know. It describes what we are not allowed to know. There is no hidden layer where position and momentum coexist with infinite precision, waiting to be revealed. That layer does not exist. Nature does not store exact values and refuse to share them. It never assigns them in the first place. This is the part that breaks classical logic. Classical physics assumes that properties exist independently of observation. A thing has a position, it has a velocity. Whether or not you measure them is irrelevant. Quantum mechanics rejects that assumption. Certain pairs of properties are mutually exclusive in their precision. Defining one sharply makes the other undefined, not blurry, not unknown, but meaningless in the classical sense. Uncertainty is not about ignorance, it is about incompatibility. And once this is understood, a deeper question emerges. Why would the universe be built this way? Why would reality impose such a strange restriction on knowledge? Here is the twist. If uncertainty did not exist, nothing else would either. Without uncertainty, electrons could fall directly into atomic nuclei. There would be no stable orbits, no electron clouds, no separation between matter and collapse. Atoms would implode, chemistry would vanish, biology would never arise, stars would not burn in stable cycles. The very structures that make complexity possible rely on this fundamental spread in particle behavior. The probabilistic nature of electrons prevents them from occupying a single fatal point of certainty. Their uncertainty gives atoms size, shape, stability. Certainty would be catastrophic. Uncertainty is not a flaw in the universe's design. It is the design. This overturns classical intuition completely. We are trained to believe that order comes from precision, from exactness, from rigid control. That uncertainty is a threat to structure. Quantum reality shows the opposite. Order emerges because uncertainty exists. The stability of matter is not enforced by strict determinism, but by constraints that prevent collapse. The universe survives because it refuses to be perfectly defined. At the deepest level, reality is not a machine that demands exact inputs. It is a system that balances possibilities. This is why the uncertainty principle is not a footnote in physics textbooks. It is a statement about how existence avoids self-destruction. The universe does not tolerate absolute certainty because absolute certainty would eliminate complexity, and this realization forces a philosophical shift. Classical logic tells us that knowledge increases by narrowing uncertainty. Quantum logic tells us that some uncertainty is not only unavoidable, it is essential. The world is not ordered despite uncertainty. It is ordered because of it. This principle did not merely reveal a limit to measurement. It revealed a rule of survival written into the fabric of reality. Uncertainty is not the enemy of knowledge. It is the condition that makes a knowable universe possible at all. And once that is understood, the question is no longer why uncertainty exists, but how we ever expected the universe to function without it. So, what does all of this mean for the future of physics? Once we accept that uncertainty is not a mistake, but a fundamental feature of reality, the question stops being how to eliminate it and becomes how to use it. Modern physics does not fight uncertainty, it exploits it. One of the clearest examples is quantum computing. Classical computers are built on certainty. Bits are either 0 or 1. Every operation follows a deterministic path. The power of the machine comes from speed and scale. Quantum computers work differently. They rely on superposition, the ability of quantum systems to exist in multiple possible states at once. Instead of eliminating uncertainty, quantum computation harnesses probability. A quantum bit does not represent a single value. It represents a range of possibilities, weighted by probability amplitudes. Computation becomes a controlled exploration of uncertainty. Without the uncertainty principle, superposition would collapse into definiteness. Quantum computers would lose their advantage. The very phenomenon that makes them powerful would disappear. Uncertainty is not an obstacle to progress here. It is the engine. The same is true for quantum cryptography. In classical encryption, security is based on complexity. Codes are safe because they are hard to break, not because they are impossible to observe. Quantum cryptography is different. Its security is guaranteed by the laws of physics themselves. Any attempt to intercept or measure a quantum key inevitably disturbs it. The act of observation leaves a trace. This is uncertainty in action. Because measurement alters the system, eavesdropping cannot be hidden. The probabilities change. The intrusion is detectable. Without the uncertainty principle, this guarantee vanishes. There would be no physical way to distinguish between secure transmission and silent interception. Here again, uncertainty is not a weakness, it is protection. Then there is quantum sensing, one of the least discussed, but most profound applications. Quantum sensors are designed to operate at the edge of uncertainty. They use the limits imposed by the uncertainty principle to detect changes so small they would be invisible to classical instruments. Tiny shifts in magnetic fields, minuscule variations in time, subtle distortions in space. By pushing systems to their uncertainty boundaries, physicists amplify sensitivity. The same limits that restrict knowledge also define maximum precision. Without uncertainty, these limits would not exist, and neither would the remarkable sensitivity that comes from approaching them. In all three cases, computing, cryptography, and detection, this principle is not a theoretical inconvenience. It is a resource, a constraint that becomes a tool. This marks a profound shift in how physics progresses. Instead of trying to restore classical certainty, modern science builds technologies that assume uncertainty is permanent. Progress no longer means eliminating ambiguity, but navigating it intelligently. And this brings us to why this idea still matters today. Its contribution was not just an equation, it was a philosophical reorientation. Quantum physics forced science to abandon the idea that reality can be fully known, not eventually, not with better theories, not with infinite precision. Every model is partial. Every description leaves something out. And this is not a failure of science, it is its boundary. The uncertainty principle reminds us that no theory is the final word. There will always be aspects of reality that resist total capture by equations. This humility is not weakness, it is intellectual honesty. Classical physics promised certainty. Quantum physics offers reliability without completeness. It tells us what can be predicted, and equally importantly, what cannot. It also reminds us that certainty is a privilege of the macroscopic world. At human scales, uncertainty fades into insignificance. Objects behave predictably. Trajectories look smooth. Causes lead to effects with reassuring consistency. This is not because uncertainty disappears, but because it averages out. At the quantum scale, there is no such comfort. The universe speaks in probabilities. It whispers through wave functions, and when asked a direct question, it responds with a range, not a point. This refusal is not a flaw in nature's design. It is the design. A universe that offered perfect certainty would be static, fragile, and simple. A universe that embeds uncertainty can sustain complexity, stability, and growth. This principle shows us that limits are not always obstacles. Sometimes they are the very conditions that make progress possible. And as physics moves forward into deeper theories, new technologies, and stranger realities, this lesson becomes more important, not less. The future of physics will not be built on eliminating uncertainty, it will be built on understanding why the universe needs it, and learning how to listen when reality answers probabilities instead of certainties. If there is one idea worth carrying with you after this video, it is this. Uncertainty is not a failure of science, it is one of its deepest truths. Quantum physics did not take certainty away from us. It showed us why the universe never owed it to us in the first place. And as physics moves forward, as technology advances, and as our questions grow more ambitious, this principle remains unchanged. Some limits cannot be crossed, only understood. If you found value in this exploration of science and philosophy, support the channel by liking this video. It helps these ideas reach people who are searching for more than simple answers. Subscribe if you want more deep dives into the ideas that reshaped reality. Videos where physics meets philosophy and where questions matter more than conclusions. And leave a comment below. Do you think uncertainty is a limitation or the very reason the universe works at all? Thank you for watching. And remember, when reality refuses to give a clear answer, it may be telling you something far more important.